This is the lecture for section 6C on the normal distribution. The normal distribution, as we've seen, is a symmetric, bell-shaped distribution with a single peak. The peak represents the mean, median, and mode of the distribution. Its variation then is characterized by the standard deviation of the distribution, which we talked a little bit about in the last section. Below here are two distributions. The first one is a famous data set of the chest size of 5,738 Scottish militiamen collected in about 1846. And B is the distribution of the population densities in 50 states. Which of these is the normal distribution, and can you explain? Here's a great slide for you guys to add a comment to. Which one is normal? Why do you think that is? And what shape is the other one? Hopefully some of you tried to answer the question on the last slide. But here's the thing. Chest size, something that we can measure on human beings, is going to be the normal distribution. So that first graph is that normal bell-shaped curve. And the one on the second graph, the one on the right, is going to be very, very right skewed. So did you get it right? I hope you did. The following are some conditions for our normal distribution. Basically, if you have all of these things, it's probably going to be a normal distribution. The first is that most of your data is going to be clustered right near the mean, which is what gives us that single peak right in the middle. Data values then are going to be spread evenly around the mean. So we are going to have the same above, the same below, resulting in what looks like a symmetric graph, a graph I can cut in half, and I see the same on both sides. Larger deviations from the mean are increasingly rare, basically meaning that the farther I get away from that peak, the less likely this to occur. The shorter my bar is going to be, the closer I'm going to be to my axis. And individual data values result from a combination of many different factors. I'm going to give you two examples here, and only one of them is going to be a normal distribution. Which of the following would you expect to be normal or normally distributed? Scores on a very easy test, or foot lengths of a random sample of adult American women. Well, I've always mentioned from the beginning, if you are going to measure something in regards to humans, that is going to give you a normal distribution. So you should know right away that that second one's going to be our normal distribution. Now, here's another thing to think about. That first one, a very easy test. Well, if it's a very easy test, you can expect that most of the people are going to do very, very well on that test, and you may only have a random one or two that don't. So you'll have a lot of people scoring, here's like my 90s and 100s, and then you may have somebody down here who really didn't pay any attention and got like a 50. So it's going to be a lot skewed to the left because most of my values are going to be right around that maximum score. As I mentioned on the previous slide, foot length is a human trait that we are going to measure. Anytime we measure something like that, we can gather information that most of them are going to be right around that mean value, but then you're going to have some slightly bigger feet, some slightly smaller feet, and we should expect any form of measurement on human beings to have a general normal bell shape. Anytime we work within our normal curve, we have what's called the 68, 95, 99.7 rule. And what that means is we can estimate percentages that are going to be within certain ranges of our data set. So what you'll always do is anytime you're asked for these types of questions, you're going to draw your normal curve with the mean in the middle. You're going to go 3 standard deviations up, 3 standard deviations back. The 68% is the on average, this is usually what we expect to happen, 68% of our data should fall between 1 standard deviation. 95% is going to fall between 2 standard deviations, and then 99.7 is going to fall between 3 standard deviations. Some other things to note is that when we work with these, all of these can then be split up. So if I've got 68% between here, I can break it in half. That's 34% on this side and 34% on this side because it is symmetric. The entire area is also equal to 100%. So if I've used 68%, I could take 100 minus 68, and then I have 32% left over, which means that there would be 16% on this side and 16% on this side. So we can do a little bit of basic math to figure out, oh, that's 34% of my data should be between here, or 16% would be between these two values. So that's kind of where we're going to go here in just a minute. About 68%, if you want to be exact, it's 68.3%, or just over 2/3 of our data is going to fall within 1 standard deviation of the mean. So 1 standard deviation up and back, we're going to generally say 68%. 95% is going to be between 2 standard deviations. Again, if you want to be a little more precise, it's actually 95.4%. We're going to average 95. We're going to use 68, 95, 99.7. Those are the 3 values that we are going to use. Some textbooks do use those decimals. Ours, we're not. The last one is 99.7 for the 3 standard deviations. This rule applies to anything that is a normal curve exactly 1, 2, or 3 standard deviations away. If it's anything besides exact numbers 1, 2, 3, this rule does not apply. Have you ever walked up to a vending machine, put some of your coins in, and it spits them right back out? Well, this is why. Vending machines can be adjusted to reject coins above and below certain weights. The weights of legal U.S. quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? So there are actual systems in these vending machines that weigh these quarters, and if they think it's not within normal range, it spits it back out. Now, when I go to do these problems, I will usually draw my number line here, and I'll put the mean in the middle. So the mean we said was 5.67. And what I'm going to do is then do my standard deviation. I'm going to add it 3 times and then subtract it 3 times. So I'm going to go up 1, 2, 3, go back 1, 2, 3. My standard deviation was 0.07. So if I take 5.67, I'm going to add 0.07 and 0.07. I'm going to get 5.74 for the first one. I'm going to take that value. I'm going to add 0.07, gets me 5.81. And I'm going to add it one more time. And I'm going to get 5.88. Now I'm going to do the same thing, but now I'm going to go backwards. So now I need to go backwards 0.07. So if I take 5.67 minus 0.07, I get 5.60. And then if I take that value minus 0.07, 5.53, And if I go back another 0.07, 5.46. So I will always draw my number line when I'm doing these problems. Now, it said we're going to reject quarters that are above 5.81, so above those, and below 5.53. So a weight of 5.81 is 0.14 grams or 2 standard deviations above the mean. Here's our mean, 2 above. A weight of 5.53 is 0.14 grams or 2 standard deviations below the mean. So what it's going to do is it's going to accept the quarters between these two values. So we'll accept anything between 5.53 and 5.81. And according to that rule that we just discussed, 2 standard deviations is 95%. So we're going to accept 95% of the quarters that get put into the machine. But then the question asked what percentages of them will be rejected. Well, if we accept 95%, then 5% of them will be rejected. We're going to do a few more here. The resting heart rate for a sample of individuals is normally distributed with a mean of 70 and a standard deviation of 15. Use the 68, 95, 99.7 rules to evaluate the following. So I'm going to start with my number line here and put my mean in the middle. I'm going to put 3 tick marks up, 3 tick marks back. The tick marks are evenly spaced because every tick mark is going to have a difference of 15. So if I'm going to the right, I'm going to go up by 15. If I'm moving back to the left, I'm going to go down by 15. So I'll start by going up. 70 plus 15 is 85. Add 15 again is 100. Add 15 one more time is 115. And then if I want to go backwards, subtract 15, that's going to get me 55. Subtract 15 again is 40. Subtract 15 again is 25. So the first question says, what percent could I expect to have greater than 100? So what I'm going to do here is I'm going to find my 100. So here's mean, 1 standard deviation, 2 standard deviations, 3. 1 standard deviation, minus 2 standard deviations, minus 3 standard deviations, because I went back. All right, so we know that between 2 standard deviations is 95%. We know that. So that leaves 5% that's outside. Well, if I only want this side here, I need half of that remaining 5%. So it's 5% between the two sides that are left over. So half of it's going to be on each side. So 2.5% are going to be greater than 100. So let me explain that again. 95% of our values are between 2 standard deviations. That leaves 5% remaining outside. If I only want one of the sides, I want half of that data, or 2.5%. Next one says less than 85%. Well, here's 85. Let me grab a different color. 85 is one value above the mean. And in the graph, I said it's between 1 standard deviations is 68%. And there's 34 on each side. 34 on this side, 34 on this side. Makes our total of 68. Here's the other piece that I know. The mean is the exact middle. So this side makes up exactly half of the data. So here's 50% of the data. And then I want to add this next 34%. So 50% plus 34% makes a total of 84%. Next one. Less than 40. So let's see, 40 is, that's going to be the same as this 100. So let's take a look here. Okay, 40 and 100 are both 2 standard deviations away. So we found greater than 100 was 2.5% here. So that means on this side should be the other 2.5% for less than 40. And then our last question says between 55 and 85. So 55 and 85 is 1 standard deviation up and back, and that is exactly 68%. So you're going to work with those values, work with the hundreds, work with the fact that these are symmetric, and you can always separate them out. Another one that I could have asked you, let's say greater than 85. So I could have done that by knowing, here's the mean, and here's 85, 1 standard deviation above. So we know between 1 standard deviation is 68%, which leaves, we showed this on the other slide, 32%. So 16% on this side and 16% on this side. So 16% would be above that value. It also means that there's 16% below 55. It's all symmetry that happens in this normal curve. Now, sometimes what happens though is the values that we look at are not exactly 1, 2, or 3 standard deviations away from the mean. So what we can do is we can calculate what is called a z-score. The other purpose of this is so that we can compare across more than one data set. It gives us a standard to look at, and it tells us how far this specific value is above or below the mean. So we can calculate a z-score by taking the data value in question minus our mean and take that result divided by the standard deviation. If our result is positive, we are going to be that many standard deviations above the mean. If that value is negative, it's going to tell me how many standard deviations I am below the mean. The Stanford-Binet IQ test is scaled so that scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the standard scores for IQ scores of 85, 100, and 125. What we're going to do is we're going to do all 3 of these, calculating using the formula, take the data value minus the mean of 100, and then take that result divided by 15. Starting with 85. So our data value is 85. We subtract 100. That is going to give me negative 15, which I divide by 15 and I get negative 1. So 85 is exactly 1 standard deviation below the mean. Our standard score for 100, well, this should make sense here. 100 is our value minus 100. This is the exact mean. If I take 0 divided by 15, I get 0. So this is nowhere from the mean. It is the mean. Our standard score for 125, you'll take 125 minus the 100, gives 25. 25 divided by 15 is 1.67. So this means we are 1.67 standard deviations above the mean. So if I were to look at my, my graph here, I start with 100, I go by 15. So 115, 130, 145. We know that 125 is over here. It's not an exact value, so we use the z-score to tell me exactly where it does fall. So it is 1.67 standard deviations above the mean. So it's between 1 and 2 standard deviations. It is up here. So it's a great way just to tell us where these values fall, especially if, like I said, we're comparing or we don't have the exact 1, 2, or 3 standard deviation values. The other reason I mentioned using a z-score is so that we can compare across 2 different groups. Let's say in your math class you scored a 90% on the recent test that had a mean of 82 and a standard deviation of 5. In your writing class you scored 86% on a test that had a mean of 80 and a standard deviation of 2%. Which class did you actually do better? So you may say right away, well, I scored a 90%, so I did better on that one. The goal is we want to see how you did compared to the rest of the class. So which did you actually do better compared to the rest of the class. So we have to figure out how we did relative to everybody else. So I'm going to start with math. I scored a 90. The mean was 82, and the standard deviation was 5. So if I take 90 minus 82, that's 8. 8 divided by 5 gives me 1.6. So I am 1.6 standard deviations above average. You should be able to see that. 90 is above 82, so I know I did better than the average of the class. But how much better? And is it different than my writing class? Well, in writing, I got an 86. The average was 80, and the standard deviation was 2. So if I take 86 minus 80, that's 6. Divided by 2, I get 3. So in this one, I'm 3 standard deviations above the rest of my class. So I actually did better compared to the rest of my class in writing than I did in math. Now, my overall score, I got an A on my math test, only a B on my writing test. So you always have to be careful what you're looking at. Comparatively, though, in this one, writing was better. The last thing that goes along with these standard scores is percentiles. Anytime you take a standardized test, you got a little printout that said you scored in the 82 percentile. Well, what does that actually mean? The percentile that you got, that tells you how many people scored below you. So if you scored in the 82nd percentile, you did better than 82% of it, the other people that took that. And then there were 18% of people that were above you. So anytime you're given the percentile, so whatever percent, such and such percent, let's say 52. This is how many scored below you. So 52% were below your score. And then the remainder to get to 100, so 48% are above you. Same thing that happens if you have children or you go and get them for their first few years of life. They keep track of their weight, what percent they're in for weight, height, head circumference, things like that. So what does it mean if you score in the 80th percentile on a test? Well, it means you scored better than 80% of people who took the test. But that also means that 20% of people did better than you. Okay. This is the end of this week. You have Pearson homework for 6B and 6C, as well as a discussion board. And this concludes both chapter 5 and 6. So next week, you will be taking a test over these 2 chapters. See you back here in a week or 2, and I will be moving on to chapter 7.